First we start equivalence class and partition. This portion we know about that a relation on a set is a subset C of Cartesian product A cross A or A Cartesian product A. A relation is the subset C of A Cartesian product A, and an equivalence relation on a set A is a collection C on A having the following three properties: first, reflexivity; second, symmetry; third, transitive property. That means an equivalence relation on a set A is a relation C on A having those three properties. Now we discuss about equivalence class. Equivalence class delta be an equivalence relation on a set A. That means this relation satisfies reflexive, symmetry and transitive property, and this relation must be subset of A Cartesian product A. We define a certain subset E of A called equivalence class determined by X by the equation E such that those Y related to X. Okay, those Y related to X. Now define an equivalence class. One relation 1 1 1 2 2 1 2 2. This is the relation and subset of A Cartesian product A, where A equal to 1 2. Then here this delta B equivalence relation, delta equivalence relation on A. Now X belongs to A, that means 1 belongs to A. 1 is related to which element? 1 is related to 1 and 2. So 2 elements. So these two form a equivalence class. Okay, these two form a equivalence class determined by 1. This one is the equivalence class determined by 1, and also 2 belongs to A. Then 1 2 is related. This one be the equivalence class determined by 2. Just some X belongs to A, one subset of A called equivalence class. One subset of A called equivalence class determined by A by the equation E equal to those Y related to X. Okay. Now we understand this. That means first we study about relation is a subset. Relation is the subset of a Cartesian product A, and second an equivalence relation. An equivalence relation obviously subset of a Cartesian product A and obviously follows reflexivity, symmetry and transitive properties. And then equivalence class is subset of A determined by those element of A which is related to another elements in equivalence relation. Okay, so we understand properly. Now we start with those two equivalence classes by this lemma. We starting by this lemma. Two equivalence classes are disjoint. Or equal. Two equivalence classes are disjoint or equal. Let E be the equivalence class determined by proof. Let E be the equivalence class determined by X. And let just be the equivalence class determined by X test. Okay. Then suppose E intersection E dash not, not equal to phi. Then let Y belongs to E intersection E dash. That means that is Y related to X and obviously Y related to X dash. Now by symmetry X related to Y and Y related to X dash this, and by transitivity X related to X dash. Okay. Now X related to X dash. So we now start. We have to show that E equal to E dash. Obviously, if this one happen not equal to 5, so we have to show that E equal to E dash. Okay. Then by symmetry this one, by transitivity this one. Now we discuss about a point WB belongs to E. Okay. E with the equivalence class determined by X. Now W is related to X. Okay. And it follows from the application of transitivity that obviously by transitivity W is related to X dash. Then we conclude that E subset of E dash, because W belongs to E implies that W belongs to E dash. Let W belongs to E, and then this one. And obviously conversely, in the same way, if we let P belongs to E dash, then P related to X dash by transitivity P related to X. This implies that P belongs to E. This implies that E dash subset of E. So E equal to E dash. Okay, understand? So two equivalence class. Equivalence class are those which are one element related to another element, and this from subset of the set. Okay, then these equivalence classes are disjoint or equal. Okay, here equal, if equal to E intersection E dash equal to 5, then they are disjoint. So today we discuss about that two equivalence classes are disjoint or equal. Now we discuss about next partition. Partition are those. Definition of partition. Partition of a set. A partition of a set A A partition of a set A is a collection of disjoint non-empty subset of is a collection of disjoint non-empty subset disjoint non-empty subsets of A whose union is equal to A. Okay, now we start by some example, some trivial example of those numbers, that means A related to B if and only if A minus B divisible by 5. Okay, where A B belongs to Z. Then with 0 class, 1 class, 2 class, 3 class, 4 class. All class are from now. Now 0 class element are 0, 5, 10, dot dot dot. 1 class element are 1, 6, 11, dot dot dot. 2 class element are 2, 7, 12, dot dot dot. 3 class element are 3, 8, 13, dot dot dot. 4 class element are 4, 9, 13, dot dot dot. Okay, so in this way we obtain those are the partition. That means we create this one is the equivalence classes and form some partition. That means these are all partition of this equivalence. These are 5 distinct equivalence classes. Okay, and those equivalence classes forms a partition. Now also we determined by some trivial example. Trivial example is those 1 1 1 2 2 1 2 2. Okay, here we construct one if we construct this one is the delta and a equal to 1 2 and then 1 belongs to a, this 1 2 are related, 1 2 be some partition. Okay, 1 2 non-empty subset of A which are related to 1, and obviously 2 belongs to A, then 1 2 are related to 2, then these two here, these two partitions are same because one common element is there. That means partitions are equal or disjoint. Here equal partition found. Okay. Now we discuss about some example of partition. Example of partition, we start about 2 points in a plane, 2 points in a plane, to be equivalent, two points in a plane to be equivalent. Two points in a plane to be equivalent if they lie at the same distance from origin. If they lie the same distance from the origin. The same distance from origin. Then the equivalence classes are different radius circle whose center is origin. Okay, and they are all partitions of the given set. So today stop here.